Hello and welcome to the Aakash BYJU's JEE channel. My name is Atiullah and we are live once again with JEE Mission 2022. So before we start, just let me know if you can hear me properly and you can see me clearly. Alright, hi guys. Hi, good evening Captain Jack Sparrow, one of the most regular people on this session. Hi AK Technology, hi Shubham. How is it going? Alright guys, just let me know if you can hear me and see me clearly and then we'll get started with this session. Dinesh, I do teach in English, so that should not be a problem. Cool guys, can you hear me? Hi Maths Education, how is it going? Alright guys, perfect. So, we are live once again with JEE Mission 2022 and the topic for this time is moving charges and magnetism. Okay, moving charges and magnetism is a part of electromagnetism and it is one of the most high ROI chapters in the whole of physics. Okay, modern physics is the most ROI chapter. ROI, you know, means return on investment. Similarly, moving charges and magnetism, this entire topic, electromagnetism, is very scoring. It's a gift from JEE to you, and if you prepare this well, it's very scoring. Alright, so this should be a very important revision session for you. Alright, more people joining in. Hi Mr. Unknown, hi Raj, hi Anirban, how is it going? Alright, so you know the drill, how we go about it. I'm going to throw questions at you and you're going to tell me that what is the concept. Okay, the most important discussion is not the solution here. The most important discussion in these sessions is the concept. So you're going to first tell me what is the concept that is involved, and once we are past that, we are going to solve the question as well. Alright guys, are you ready? So if you guys are ready, then let's get cracking with this session, and here is the first question for you. Okay. One more thing before we start this session, important announcement. At 8:30, I'm going to come live once again and we're going to talk about the breaking news about CBSE term 2 pattern. Okay, so do tune in at 8:30 again. Very important announcement, and that is going to impact your board's preparation. So do tune in, but let's get back now to the agenda at hand. Okay, so let's start with the first question, and here's the first question for you. A positive charge q of mass m is moving along the x-axis. We wish to apply a uniform magnetic field B for time delta t so that the charge reverses its direction, crossing the y-axis at a distance d. Then, if we look at the options, what do we need to calculate? We need to calculate the magnetic field and we need to calculate this time interval delta t. Okay, that's the question. Take a few seconds to absorb the question and tell me what is the concept that is involved over here. Quickly tell me the concept and then we are going to move ahead with the solution. Okay, the objective of all these sessions is to revise the concepts. If the concepts are good, perfect, but if they are weak or if you have forgotten something, then we should always brush that up. Alright, so Maths Education is asking, will you cover theory in this video? We are not covering theory, but whenever we are solving the problem, we are discussing what is the concept involved. Okay, so you're not just getting the solution, you're getting what is the concept behind that. Any discussion related to that concept is going to be here. Okay, alright, now let's look at the question here. So a particle is moving along the x-axis. Alright, it is moving along the x-axis like this. Now we have to apply the magnetic field such that it reverses its direction. Okay, which means when it is crossing the y-axis, then it has to reverse its direction, and this distance here has to be d. Okay, so the question is, how should we apply this magnetic field? Okay, so what is the concept here? Yes, Captain Jack Sparrow is absolutely right. Magnetic force. When we have a moving charge particle in a magnetic field, it experiences a force. Is that right? But a very special case is when the velocity and magnetic field is perpendicular to each other. In that case, there's a very special kind of trajectory that the particle takes, and that trajectory is, yes, that is going to be a circular trajectory. Is that right? Okay, so I should apply a magnetic field perpendicular to the velocity, that's for sure. I should apply the velocity perpendicular to the velocity. Otherwise, it is going to be a helical path. Okay, if I have velocity and magnetic field at a certain angle which is not 90 degree, then you know that the path of the particle is going to be helical. We don't want that over here. We want a simple circular path to connect these two. Is that right? So if this becomes a semicircle, then my job is done. Okay, so all I have to do is to make this path, make this particle go in a semicircle. That's all I have to do. So I have to apply a magnetic field which is perpendicular to the velocity. Now can you tell me what should be the direction of this magnetic field? Okay, the direction of force on a moving charge particle in a magnetic field, how do we figure that out? Can you tell me what will be the direction of the magnetic field? Or I should reframe my question, what should be the direction of magnetic field such that this particle takes this particular trajectory? Can you tell me? I'm going to wait for your answer. Okay, so in magnetism and in electromagnetism, you'll see there are a lot of questions where the direction is very, very important. Okay, we'll have to calculate the direction of the force, we'll have to calculate the direction of the magnetic field created by current. Okay, so we'll have to be very careful and we have to be very confident about how do we figure out the direction. Okay, so the force on a moving charge particle is QV cross P. We know that. So all we have to understand is the cross product between velocity and magnetic field. Okay, so if we choose the magnetic field like this, going into the plane of the screen, yes, you guys are absolutely right. The magnetic field should be going into the plane of the screen so that the force is going to be in this direction. So wherever is the particle, the force is always going to be pointing towards the center. That will be the centripetal force. Is that correct? Perfect. So now what we have to do is we have to calculate this magnetic field. Okay, we have to calculate the magnitude of this magnetic field. Now that's very simple. So if this is a semicircle, then there has to be a center. And if there is a center, then there has to be a radius. Okay, what is the radius of this trajectory? Can I say that the radius of this trajectory is d by 2? Okay, and we know that the radius of the particle, when we have a charged particle under the influence of a magnetic field which is perpendicular to it, the radius is given by mv upon qb. Do we know this? Of course we know this, right? If you don't know this, make a note of it, go back and revise. Okay, so what is the radius over here? The radius over here is d by 2 and that is going to be equal to mv divided by qb. What does it mean? It means that it is going to give me the value of b. The value of b is going to become 2mv divided by qt. Is that correct? Absolutely, absolutely. Okay, perfect. So we have calculated what is the magnetic field. What we also have to calculate is the time it takes. Okay, so what is the time? So if it would have been a complete circle, the time taken would be equal to the time period. But if it is only half a circle, then what will be the time taken? The time taken is going to be half of the time period. Okay, so what is the time period of the complete revolution? The time period of revolution is 2 pi m divided by qb. Is that right? So the time taken in this case is going to be half of that, so that is going to be pi m upon qb. But we have to give answer in terms of the things which are given. Okay, so we don't have b, but we have calculated b over here, so we're going to make a substitution. So this becomes pi m upon q, and for b I'm going to substitute 2mv, and q and d are going to go upstairs. This m gets cancelled, this q gets cancelled. So what do I have? I have these answers. B is equal to 2mv upon qd and delta t is equal to pi d upon 2v. Is that correct? Alright, just gaming, if you're not able to see the screen, I think it is clear for everyone, so just try refreshing your device. I think it should be fine. Alright, don't worry about it. Just try refreshing the screen. Alright guys, is that clear? Okay, a simple answer, simple question to start off, but obviously we're going to have more interesting questions. Alright, what is the takeaway? What is the concept? The concept is that the radius is going to be mv upon qb and the time period of that circular path is 2 pi m upon qp. Is that correct? Clear? All good? All of you guys, I hope, are warmed up. So now let's go to the next question. All right. Before that, option C is going to be the right option, of course. And now we go to the next question. All right, here's the next question for you. The circuit in figure consists of wires at the top and bottom and identical springs as the left and right sides. Okay, can you see the diagram? Okay, so we have a battery, we have a resistance, and then we have a wire, and that wire is suspended by two springs, and those springs are conducting as well. Now the wire at the bottom has a mass of 10 gram and is 5 centimeter long. The wire is hanging as shown in the figure. The springs stretch 0.5 centimeter under the weight of the wire, and the circuit has a total resistance of 12 ohm. Okay, so initially the wire, the weight of the wire is going to act, and because of the weight of the wire, the spring is stretched, both the springs are stretched by 0.5 centimeter. Okay. Now when the lower wire is subjected to a static magnetic field, the springs stretch an additional 0.3 centimeter. The magnetic field is, okay, so in this region a magnetic field is switched on, which is static, meaning which is constant, and then the springs stretch a little bit more, okay, by how much? By 0.3 centimeter. Is that right? That is the question. So what do we have to calculate here? We have to calculate the magnetic field. And if you look at the options, we just don't have to calculate the magnetic field magnitude, but we also have to calculate its or figure out its direction as well. All right. This is the question, and I'm going to throw it to you, and I'm going to ask you, what is the concept that is involved over here? What is the concept involved in this question? How do we proceed with this question? What is the first thing that comes to your mind? That's what we need to discuss. Okay. Once we have that clear, once we know what concept is going to be applied, then finding out the solution is not really difficult. The first step is the challenging step, when you have to figure out, when you have to decode the question and figure out what is it that we're going to use in this question. Is that right? That should be your strategy always. Okay, so guys, tell me, what is the concept involved? Balance net force. Shubham is saying balance net force. You're absolutely right, Shubham. We are going to balance net force, but what force are we talking about? What are the forces which are in picture? What do you know about those forces? Alright, so let's take the first scenario. Okay, so the spring are stretched. Let's say this was the natural length, and the spring are stretched by x naught. Okay, x naught is 5.5 centimeter. Okay, the spring is stretched by x naught. What are the forces acting? The first force that is going to be acting is mg. Okay, and what other forces are going to act? The other forces are going to be kx naught from this spring and kx naught from this spring. Is that right? And obviously they are going to be in equilibrium, so 2kx naught should be equal to mg. Is that correct? That is the first relationship we have got. 2kx naught should be equal to mg. Is that correct? Okay. Now when the magnetic field is there, okay, so what we are seeing here is that there is a battery, there is a resistance, so, and the circuit is also complete, and if the circuit is complete, obviously current is going to flow. And how much current is going to flow? Current flowing here is going to be 2 ampere. Can you see that? 24 volt battery, 12 ohm resistance, the current that would be flowing is 2 ampere. Is that correct? Okay. And whenever we have current in a magnetic field, what happens? The current carrying conductor experiences a force. Is that correct? What force does it experience? Do you remember what force is experienced by a current carrying conductor? Okay, the fundamental equation here is I dl cross B. Do you remember this? Okay, we generally start memorizing this result as ILB, 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 but we forget sometimes that what is the fundamental equation behind that. Okay, so df is equal to I dl cross P, and if magnetic field is constant, then the net force becomes IL cross B. Is that correct? Okay, and the wire has to be, or that's fine. For now, that's fine. But the important thing to remember is that when magnetic field is constant, only then the magnetic force becomes IL cross B. And if the direction or if the angle between the length or the current and the magnetic field is 90 degree, then the magnitude of force becomes ILB. Is that correct? Okay, so there are two special cases going on over here. Don't take it for granted. Okay, the magnetic field is constant. That is why the force becomes IL cross B. And because the magnetic field and the current or the length are perpendicular to each other, the force becomes ILB. Is that right? Okay, so obviously in this situation we're going to use ILB. So the first thing we need to figure out is what is the direction of the magnetic force. Okay, there's current flowing from left to right. So there is mg already, but the spring stretches more. Okay, the spring gets further stretched by 0.3 centimeter. Okay, so if this was the natural length, now the elongation of the spring is x naught plus delta x. Is that correct? So obviously the force would have been in this direction. Is that also correct? Okay, now the question is, the magnetic field is from left to right, the magnetic force is downwards. Can you tell me the direction of magnetic field? Okay, can you tell me the direction of magnetic field? How do we find out the direction of magnetic field? That's my question to you. Can someone tell me, from this situation, we know the direction of current, we know the direction of force, can you figure out the direction of magnetic field? Can we do that? How do we do that? Any hints you can give me? What should be the direction of the magnetic field? Outwards. Alright, Aniket is saying outwards. Are other people supporting this answer, or other people have different answers? Yes, absolutely, absolutely. Okay, so I'm going to show that to you. If someone has forgotten, it's okay, I'm going to revise that for you. So I'm going to turn this way and then I'm going to show it to you, because my left becomes your right becomes my left, so there's confusion. So I'm going to turn and I'm going to face I'm going to show you how you are seeing the screen. Okay, so what is the direction of current? The current is from left to right. Is that correct? The current is from left to right. Okay, and the force is downwards. Okay, so if the magnetic field comes out, okay, so what we have to do is we have to do L cross B. Okay, we have to do L cross B. Can you see? The force is L cross B. So the direction of magnetic field is going to be L cross B. And the direction of the current and direction of L is the same. Okay, so we have from left to right the current. Okay, and then we have the force here. So if the magnetic field is coming out, then we're going to curl it like this. Okay, we are taking a cross product. Okay, we are taking a cross product, so the force is going to come out to be in the downward direction. Okay, so obviously in this case the magnetic field has to come out of the plane of the screen. Is that correct? Okay, now once we have figured that out, calculating the value of magnetic field is not difficult at all. Okay, so I'm going to rub this off, and then now we are going to write the new equilibrium equation. Okay, let's write the new equilibrium equation. All right, now the spring has an elongation of x plus delta x. So the force exerted by one spring is going to be k into x naught plus delta x. Then there are two springs, so multiplied by 2, and this is going to be equal to F plus mg. Okay, and what is the value of F over here? The value of F over here is going to be ILB. Is that correct? The value of F here is going to be ILB. Perfect. Okay, so from here what do we get? We get 2k x naught plus 2k delta x is equal to ILB plus mg. Okay, but remember the first equation. From the first equation we had figured out that 2k x naught and mg is going to cancel out. Okay, because before the magnetic field was introduced, the weight was being balanced by the spring force. Okay, so 2k x naught is equal to mg, so they cancel out. So what do we get? We get 2k delta x is equal to ILB. Is that correct? This is my equation number 2. And what I need from here is I need magnetic field. So what I'm going to do is I'm going to take the equation 1. So what was equation 1? Equation 1 was, let's write it down here, kx naught, 2kx naught is equal to mg. That was equation 1. So let's divide equation 1 and equation 2. Okay, so let's divide them. So if we divide both the equation, we are going to get delta x upon x naught is equal to ILB divided by mg. Is that correct? Okay, so Mahesh is asking, sir, how it's cancelled out. From the first equation, Mahesh, just check the first equation, the first equilibrium condition, 2kx naught is equal to mg. Check, let me go back and show it to you. This, the first equilibrium condition, we had calculated that. Okay, so that is equation 1, equation 2 we have figured out, and then we divide both the equations and we get this. Okay, so what is the final result? The final result is going to be, okay, so now we can substitute the values also. What is delta x? Delta x is 0.3 centimeter and x naught is 0.5 centimeter. Now because both of them are centimeter, I don't worry about the unit. Okay, it's the ratio, it gets cancelled out. So this is equal to ILB divided by, okay, let's substitute, sorry. What is I? I is 2 ampere. What is L? L is 5 centimeter. So 5 into 10 to the power minus 2. And B we have to calculate. And then mg. M is going to be 10 to the power minus 2 kg. And then G is going to be 10. Is that correct? Okay. So that is going to be my equation. And if we solve all of this, okay, simple calculation, if you solve this, you're going to get B is equal to 0.6 Tesla. Is that clear? Okay. So we calculated the first equation from the first equilibrium condition. We calculated the second equation from the second equilibrium condition. We divided the equations and then we found out what is the value of magnetic field. Okay, it is going to be 0.6 Tesla and it is going to come out of the plane of the screen. Is that correct? Is that clear? Okay, so I hope it's clear. And the important concept we learned here was, what is the force on a current carrying conductor in a magnetic field? Okay, and what are the special conditions? And because of those special conditions, what is the result? What is the final result? Okay, but we should never forget the initial, the most fundamental equations. Okay, we should never forget, because tomorrow it can happen that it does not give you a uniform magnetic field. It can have a variable magnetic field, right? So we should take that in, we should keep that in mind. Okay, so Vijay is asking, is Irodov better, sir? So this is not really the time to discuss the strategy or the books, but I should tell you, Irodov is the mother of all books. All the questions that you see in all the books have fundamentally come from Irodov. Okay, but because of the pattern is not subjective anymore, it's more objective. So Irodov is not really necessary, but if you're done with everything, if you're done with all the books, all the material, and if you still have time, then of course go for Irodov. But in my opinion, given the pattern, Irodov is not really required. Okay, but if you are interested, sure, it's a great book to solve. All right, so option A should be the correct option, and then we move to the next question. All right, what's the next question? So there is a conductor which lies along the z-axis, okay, and it is between minus 1.5 meter to 1.5 meter and carries a fixed current of 10 ampere in the z direction. Can you see that? So compare the diagram alongside it, okay. So it is carrying a current in the z direction and it is contained between minus 1.5 meter and 1.5 meter, okay. For a magnetic field 3 into 10 to the power minus 4 e to the power minus 0.2 x ay Tesla, okay. So the magnetic field is a function of x. Can you see that? It has e to the power minus 0.2 x, which means it is a function of x. And what is the direction of magnetic field? The direction of magnetic field is towards the positive y direction. Can you see that in the diagram? Check. Now find the power required to move the conductor at a constant speed. 2x is equal to 2 meter, y is equal to 0 meter in 5 into 10 to the power minus 3 second. Assume parallel motion along the x-axis. So we have a conductor, current carrying conductor in a magnetic field, and that magnetic field is a function of x, it is not constant, and we have to move it at constant velocity. Okay, we have to move it at constant speed from x is equal to 0 to x equal to 2, keeping it parallel. And we have to do that in 5 into 10 to the power minus 3 second. And we have to calculate what is the power that we should deliver. Okay, is the question clear? Okay, slightly complicated question. Okay, not complicated as in the difficulty level, but there's a lot of information that is given. You have to refer to the diagram as well. Okay, so pay attention, read this question carefully, and let me know if it is clear. And if it is clear, then what is the concept that is involved? What is the concept we should use? Alright, Ranjan is asking, again guys, focus on the topics. We'll have a separate session for the books and for strategies and for material. Don't worry about that. I'll give you a short answer, but my request would be to focus on revision, the focus on the session. So Ranjan is asking if H.C. Verma is better. H.C. Verma is a great book, no doubt about that. And if you're preparing for JEE Main, it is the fundamental book you should solve. Okay, so yes, it is a very good book. Right. Captain Jack Sparrow, motional EMF. No, we don't have to go so far. You're absolutely right. There is going to be motional EMF, but we are not talking about electromagnetic induction, right? Even if there is electromagnetic induction, it's not going to have any effect over here. Okay. What we are going to understand, what we should understand here is that again there is current in a magnetic field. So if there is current in a magnetic field, it is going to experience a force. And if we have to move it with constant speed, then the net force has to be 0. So what should we do? We'll have to apply an equal and opposite force and drag it. Okay. So if we are applying force and we are displacing it, we are obviously doing work. Yes, Aman is absolutely right. We have to calculate work. So we are doing work, and divided by the time is going to give me power. Is that correct? So that is going to be the strategy to solve this question. Okay. The first question I'm going to ask you is, what is going to be the direction of magnetic force? Okay, the question is, what is the direction of magnetic force? You know the XYZ axis, you can see that in the diagram. Can you tell me what is the direction of the magnetic force? The current is along the Z direction. The magnetic field, though the magnitude is changing with the position, but the direction is the same. Alright, so the magnetic force would be in a particular direction. Is that right? So, my question is, what will be the direction of magnetic field? The direction of magnetic force. Aman, when you say upwards, do you mean the Z-axis? Okay, because you have to tell me what do you mean by upwards. So, we have X, Y, Z axis. So, if you tell me the answer in along X or Y or Z axis, then that is going to be more convenient, right? So use the axis and tell me what should be the direction of magnetic force. Z axis. All right. Captain Jack Sparrow says minus X direction. Right. So again, if we have to calculate the direction of force, then what do we have to figure out? F is IL cross P. Is that correct? F is IL cross P. So we have to take the cross product of L and B. And what is L? L is always along the direction of current. Okay, so let me turn and show it from your perspective. Okay, I'm going to show it from your perspective. Okay, so here is the current going along Z direction, and the magnetic field is, let's say, going into the plane of the screen. That is Y axis. Okay. So if we take L cross P, so what we'll have to do is, we'll have to take L cross P. So if we do L cross P, then the direction of thumb is given me the left hand side direction. Okay, which means it is along the negative X axis. The force on this wire is going to be along the negative X axis. Is that clear? Okay, so no matter where this wire is, whether it is at x equal to 0, x equal to 1, x equal to 1.5, the force is always going to be in the negative x direction. So what is the direction in which we should apply the force? We should apply the force in positive x direction. Okay, because the net force on this object, on this wire, has to be 0, because it is given in the question that we have to move it in with constant speed. Okay, so at every point the magnetic force should be equal to the force applied by us. Do you agree? Perfect. Okay, now we can see that the direction of L and the direction of magnetic field, they are perpendicular to each other. Okay, current is along z direction, magnetic field is along y direction, which tells me that force is going to be ILB. But B is going to vary with the position, so the force is also going to vary with position. But what will be the force at position x? Okay, at position x, okay, let's say between x equal to 0 to x equal to t, there is some position x. So at position x, the magnetic field would be given by this. The magnetic field would be given by this. Okay, so what will be the force? The force is going to be ILB. So I is the current, L is the length. What is the length? Let's take it L. And what is B? B is going to be 3 into 10 to the power minus 4 into e to the power minus 0.2x. When this wire is at position x, the force on it is going to be like this. Is that correct? Okay. So that is going to be the value of magnetic force. So that should also be the value of the force that we have exerted. And we are exerting force in the positive x direction. Correct? Now if we displace it slightly by dx, then what will be the small amount of work done? The small amount of work is going to be ILB into dx. Do you agree? Okay, so when let's say the wire is in this position at x, and now we are displacing by a small displacement dx, then what will be the work done? The work done is going to be the force into dx. Okay, so dw, the small amount of work done, is going to be ILB into dx. Correct? Okay, so this is going to be I. What is the value of I? The value of I is 10 ampere. The value of L is 3 meter. Alright, this is, I think this should be 3 meter. Okay, the value of L should be 3 meter, 1.5 and 1.5, 3 meter. Okay, and then what is the value of B? The value of B is 3 into 10 to the power minus 4 into e to the power minus 0.2x dx. Okay. Now if we have to calculate the net work done from x is equal to 0 to x equal to 2, then obviously what do we need to do? We need to integrate this. Is that correct? Okay, so we'll have to integrate this. So this integration is going to go from x is equal to 0 to x equal to 2. Correct? Check if the equation is correct. Check if what we have done makes sense to you. Check if you understand this. Okay, let me know if this is clear, and then we'll go to the integration part. After this, there's only mathematics. Till this point, when we are talking about physics, is this clear? The force is going to be ILB. B is a function of x. Then we displace it slightly by dx. Then the work done is going to be ILB dx. And then we need to integrate to find out the total work done. Okay, so this 10 and this is going to become 10 to the power minus 3. So this becomes 9 into 10 to the power minus 3. The work is going to be the integral of 9 into 10 to the power minus 3. And then we have e to the power 0.2x dx, and the integral is going to go from 0 to 2. Correct? Perfect. Now 9 into 10 to the power minus 3 comes out. The integral of e to the power minus 0.2x, that is going to be e to the power minus 0.2x, but divided by the coefficient of x, so that is minus 0.2. And then we have to put the limits from 0 to 2. Clear? Is the integration clear? Okay, simple integration of e to the power minus x. Alright, so this becomes 9 into 10 to the power minus 3 divided by minus 0.2, and then we have to put the limits. So e to the power minus 0.2x, I can write it as 1 upon e to the power 0.2x. Okay, so let's write it as e to the 1 upon e to the power 2x, and the limit has to go from 0 to 2. Okay, I'm sorry, 0.2x. Extremely sorry, this is 0.2x. Alright, so let's do this. So 9 into 10 to the power minus 3 upon minus 0.2 into, this becomes 1 upon 0.4x. I'm sorry, 1 upon 0.4. We have substituted x equal to 2, and then we have 1 upon e to the power 0, which is simply going to be 1. Then the question, if you go back to the question, for your calculation, for your ease of calculation, something is given. We can take e to the power minus 0.4, e to the power 0.4 as 1.5. So we are going to use that over here. So let's use that over here. Okay, so the calculation is going to become something like this. It is going to become 9 into 10 to the power minus 3 upon minus 0.2. And then we have, let's get rid of this minus sign and interchange the things which are inside the bracket. So this is going to become 1 upon 1 minus 1.5. Okay, so this becomes 9 into 10 to the power minus 3 upon 0.2. And then what do we have? So this is going to become 0.5 upon 1.5. So that is going to be 1 upon 3. Okay, so this 3 and this 3 is gone. And it gives me, but have we made a mistake somewhere? Have we made a calculation error? Oh no, we have not arrived at the answer. Okay, so this is 3 upon 0.2 into 10 to the power minus 3. Okay, so this is the work done. Okay, that's fine, that's fine. We still have to divide it by time, okay, because we have to calculate the power. So this we have calculated is this is the work done. Okay, so now let's calculate what is the power. So this becomes 15 into 10 to the power minus 3. So the power which is delivered by this force is going to be the work done divided by time. What is the work done? The work done is 15 into 10 to the power minus 3, and the time is 5 into 10 to the power minus 3. So work done 15 into 10 to the power minus 3, and the time is 5 into 10 to the power minus 3. So this is going to give me 3 watt. Okay, so the answer is going to be 3 watt. Is that clear? So the power that has to be delivered has to be 3 watt. Okay, the closest answer that we have is 2.97 watt. So that is going to be my answer. Is that clear? Is the process absolutely clear? Absolutely, Aman. The option is going to be option B, 2.97 watt. That's the closest answer to 3. So we're going to mark that answer. Okay, but my question is, what was the concept involved here? Have you revised the concept? Have you understood the concept? The concept is that there is force on a current carrying conductor. Okay, and the nature of that force is IL cross P, but we have to be careful that we can use it only when magnetic field is uniform all throughout the wire. Okay, the magnetic field has to be uniform all throughout the wire. If the magnetic field is different at different points of the wire, then we cannot use that. Then we'll have to use ideal cross P and integrate. Is that clear? Is the concept absolutely clear? And if so, then the correct option is going to be option B, 2.97 watt, and we move to the next question. All right, let's go for the next question. So here we have a wire carrying current I. It is tied to points P and Q. Okay, it's in the form of an arc. It is tied to points P and Q. It is in the shape of a circular arc of radius R. Okay, due to a uniform magnetic field B perpendicular to the plane of the paper. Okay, so what is the question? So we have a circular arc. It carries current I. It is tied between points P and Q, and there is a uniform magnetic field going into the plane of the screen, and this angle subtended over here is theta naught. The radius is R. Okay, clear? Now what is the question? The question is, what is the tension in the wire? The question is, what is the tension in the wire? Is that clear? So my question to you is going to be, why is there a tension in wire? Why is there tension in the wire? Can you figure that out first? There is tension in the wire, of course, because there's a question. We have to answer that question. But the first question that comes to my mind is, why is there tension in the wire? Suppose the points were not fixed at P and Q. Okay, suppose the wire was not tied at P and Q. Then what is going to happen? Absolutely. Captain Jack Sparrow is on fire today. Okay, he's giving all the right answers. Amazing. Absolutely right. Okay, so we have current in the magnetic field, so obviously it is going to experience force. Okay, and if there's nothing tied to it, there's nothing stopping it, then it will start moving. Okay, so the correct answer is that because there is force on the current carrying conductor in a magnetic field, obviously the points which are tied, okay, which are fixed, they are going to experience some tension because the force is going to be like this. There's going to be force in this direction. The wire will try to move in this direction, but they are keeping it there. That is why there is tension in the wire. Okay, so now let's try to solve this. So the first thing is, what is the free body diagram? So obviously the tension is going to act along the wire. So at this point the tension is going to be tangential. Do you agree? The tension is going to be like this. Now what will be the direction of magnetic field? And what will be the direction of magnetic force? And what will be the value of magnetic force? Can you figure that out? The direction of magnetic force and the magnitude of magnetic force. Can you figure that out? The magnetic field is going into the plane of the screen. The direction of current is shown to you. Now can you figure out the magnitude and direction of the magnetic force? Alright, Captain Jack Sparrow is saying upward in the plane of screen. Absolutely. Absolutely. Completely agree. And what will be the magnitude? Can you also tell me? Magnitude is going to be ILB, right? Again. But what is what is L? Can you tell me what is L that you are referring to? In the question we have R. But what is this L that you are referring to? ILB is absolutely right. I completely agree. But what is L? That's what I want to know. So L is not given in the question, so you have to tell me the value of L in terms of R. Then I'll see if you have got that right or not. Yeah? What is L? Displacement between point P and Q, and Captain Jack Sparrow is saying arc length. Okay, so we have some disagreement over here. So Captain Jack Sparrow is saying the arc length, and Shubham is saying the displacement between P and Q. So Shubham is saying this distance is going to be L. And Shubham is absolutely right. Alright, so listen up guys. So if we have a wire of non-uniform shape, okay, we have wire of arbitrary shape, and it is in a uniform magnetic field. Pay attention, uniform magnetic field, not any magnetic field. If it is in uniform magnetic field, then what we do is we connect these 2 points. Suppose this is the current, then we connect these 2 points, and then we say that whatever this length is, okay, we'll assume that the wire is of this length. Okay, so we connect these 2 points, and this vector we are going to call the L vector. Okay, simply the displacement between points P and Q, that is what we are going to call the L vector, and then the force is going to become IL cross P. Okay, that's what we should remember. Now if we have wire of non-uniform shape, arbitrary shape, then just join the 2 points, and that will be your L vector. That's it. That's all you have to understand. Okay, so if we join this is going to become L. So figuring that out is very simple. Okay, So this is r, this is theta naught, so this is going to be r sine theta naught, and this is going to be r sine theta naught. Okay, so what is the total length? The total length is going to become 2r sine theta naught. So the force is going to act in this direction, not difficult to see. Okay, so the current is going from left to right. So this pen is showing you the current is going from left to right, and the magnetic field is going into the plane of the screen, correct? So if I do an L cross B, I'll do like this, I'll do L cross B like this, and this is going to give me the direction of force, which is upward. So the force is upward. Is that correct? Okay. What is this force? This force is going to be ILB, which means it is going to be I into L, which is 2r sine theta naught multiplied by B. Correct? Now this wire is in equilibrium, which means let me draw angle theta naught over here. So this angle is also going to be theta naught. So I'm going to resolve this tension in these two directions, and we can see that this angle is also going to be theta naught. Correct? So this becomes T cos theta naught, and this becomes T sin theta naught. Similarly, this becomes T cos theta naught, and this becomes T sin theta naught. Okay, I have resolved it in two perpendicular directions, and because of that we can say that T cos theta naught and T cos theta naught are going to cancel each other out. So the net force, the net magnetic force, will be equal to 2T sin theta naught. So F is going to be equal to 2T sin theta naught for equilibrium. Okay, so from here we are going to get I into 2R into sin theta naught into B is equal to 2T sin theta naught. Correct? So from here 2 sin theta naught and 2 sin theta naught is going to disappear, and I'll be left with tension is equal to IRB. And that is going to be my answer. Is that correct? Is the concept clear? Is this concept over here, is that clear? Okay, that's the key concept over here. You take a wire of arbitrary shape, join its two ends, that is going to play the role of L. Okay, but pay attention, the magnetic field has to be uniform. In non-uniform magnetic field, you cannot apply this. Okay, perfect, all good. So what should be the correct option? The correct option should be option C. Perfect. So let's move to the next question. All right, so next question is right in front of you now. What's the question? An insulating thin rod of length L has a linear charge density rho x is equal to rho naught x upon L. Okay, the linear charge density means the charge per unit length. So the charge per unit length is a function of x. The rod is rotated about an axis passing through the origin and perpendicular to the rod. Okay, so the axis of the rotation is perpendicular to the rod and passing through its end. If the rod makes n rotations per second, then the time average magnetic moment of the rod is. Okay, can you visualize the question? Can you visualize the question? So we have this rod over here. It is moving in a circle about this axis, which is passing through its end and perpendicular to the plane of the screen. Okay, this is a charged rod and its charge density is changing. The linear charge density is variable. So at different points you'll have different linear charge density. Okay, now it is rotating, and if it is rotating we have to calculate what is the magnetic moment. Okay, now the first thing is, what is magnetic moment? Can you tell me what is magnetic moment? How do we define magnetic moment? We have to figure out what is the magnetic moment due to this rotating charge rod. But the first question obviously is, what is magnetic moment? how do we define magnetic moment? Alright, unless we know that, how do we proceed with this question? Current into area. Okay, close enough, close enough. So magnetic moment is a vector quantity and it is given by I into area vector. So if this is a loop, if it is a closed loop and there is current I, then current multiplied by this area gives me the magnitude of magnetic moment. Correct? Okay. Now, but in this question, we have a rod. We don't have a closed loop. We don't have a wire in which current is flowing. What we have is a rod, a charged rod. So the first problem is, what is the current? Okay, how do we figure out what is the current? And the second problem is, what area should we take? Okay, should we take this entire area? Should we take a part of the area? What should we do? That's another problem. Alright, do you see the problem? Do you see the problem? Alright, so the first problem can be solved by understanding that there is a charge. Okay, so if you take a small part of the rod, it will have some charge. Okay, now this charge is moving. Now if this charge is moving, then obviously the movement of charge is called current. Okay, so if this charge is rotating, it means that there is current. Okay, there is current flowing along this circle. Okay, now the problem is, there is charge over here, there is charge over here, there is charge over here. So should I consider this area? Should I consider this area? Should I consider this area? What area should I consider? That is the problem. Okay, so first problem was, how can you visualize current? So we see there is charge, the charge is moving, so there is current. The second problem is, what area should we take? Different points, the charge would be different and they will be going along different radii. So what area should we take? What's your solution? Can you suggest a solution over here? Let me redraw this. But I want to know from you, can you suggest a solution? For magnetic moment, okay, the magnitude of magnetic moment is current into area, but what area should we take? Area swept by different charges. Alright, yes Shubham, right, but what else? What else should we know here? Integration to get charge. Yes, not really. Swali, you are very close. So the thing I wanted to hear was integration, which is bang on. I wanted to hear this term integration, but not the net charge. Okay, not the net charge. Okay, so what we'll have to do is, we'll have to break this rod into small charges, and then we'll have to calculate the magnetic moment due to all these small charges, and then add the magnetic moments. Okay, so that is going to be my strategy. So what I'm going to do is, at a distance x, I'm going to take a small length dx. Okay, so what will be the charge on this small length? The charge on this small length is going to be, which I'm calling dq, that is going to be rho into dx. Do you agree? The charge per unit length multiplied by the length. So this becomes rho naught x by L multiplied by dx. Okay, so this small part over here, the small length of the rod, has some charge, and it is going to rotate in a circle of radius x. Now the next part is, how do we find out what will be the current? Okay, so what is current? The current that will be caused due to this, I'm calling it di because it's a small amount of current. So that is going to be the charge divided by the time it takes to complete one revolution. Do you agree? Okay, so in some time, through a particular cross section, okay, through a particular point, some charge is flowing. Okay, how much charge is flowing? dq charge is flowing. In how much time this charge is flowing? It is flowing in time, capital T. And what is capital T? Capital T is the time of revolution. Do you agree? Do you understand how I calculated the current? Okay, so there is a charge. Through any point, you take any point, through any point, the charge dq is going to be flowing, In what time? In time capital T. And what is capital T? The time of revolution. Okay. So the current is going to be dq upon capital T. So this becomes dq upon, and the time period I can write it as 2 pi upon omega. Can I do that? Omega is the angular velocity, and what we have here is the number of revolutions. So omega I can write it as 2 pi into n. Okay. I'm writing omega as 2 pi into n, because in single revolution it is going to rotate through 2 pi. So in 1 second, how much it is going to rotate? It is going to rotate 2 pi n. Okay, that's the angular velocity. Is that clear? So this 2 pi and this 2 pi is gone. So I get the value of di as, what is dq? dq is rho naught divided by L, and then we have n, and then we have x and dx. So we have calculated what is the current flowing due to this small charge dq. Clear? Notice I have removed, I have replaced small n by capital N, because sometimes, because of my bad handwriting and because of a lot of other people's bad handwriting, small n and x gets mixed up. Okay, so whenever I'm using small n and x, I generally replace small n by capital N. Okay, that's what I have done to remove confusion. Okay, we'll replace it back. So what I have done is I have calculated what is the current. Now this current is going around, and what is this area enclosed? The area enclosed is pi x square. What is the radius in which it is moving? Radius x. What is the area? Area is pi x square, which means that the small amount of magnetic moment due to the small amount of charge is going to be di into pi x square. Do you agree? So I can write d mu is equal to di, which is mu naught upon L into n into x dx, and then multiplied by pi x square. Is that clear? After this, you know what we have to do. We'll have to integrate. Okay, we'll have to integrate, and x is going to vary from 0 to L. Do you agree? X is going to vary from 0 to L, and then we are going to get the total magnetic moment. And we are able to add the magnetic moments, all these small magnetic moments, because they are in the same direction. Okay, so if this is the direction of current, okay, if this is the direction of current, then we are going to curl our fingers along the direction of current. Okay, and then this thumb is going to give me the direction of magnetic moment. Is that clear? Okay, so the magnetic moments due to all those charges are going to be are going to be in the same direction, so we can directly add them. Okay, so d mu is going to be mu naught. So let us rearrange these terms and finally integrate. So this becomes pi mu naught, pi rho naught n upon L, pi rho naught n upon L, and then we have x cube dx, and mu is going to be the integral of this. Clear? Okay, so this is going to go from 0 to L. Alright, let me check if I have done this correctly, otherwise I don't want any error. So rho naught n upon L and pi, and then x cube dx. Alright, so this is a no-brainer. So this becomes pi rho naught n upon L, and the integration of x cube is going to be x to the power 4 by 4. Put the limits, you're going to get L to the power 4 by 4. So this L and 1 L is going to go away. So we are going to get mu is equal to pi rho naught n L cube divided by 4. That is going to be our answer. Is that clear? Is the concept clear? Okay, so this is a genre of problem. Okay, it's a very frequently asked kind of problem, where you have to calculate the magnetic moment, and we have a rod over here. Now this rod can be replaced by a ring, this ring can be replaced by a disc, this disc can be replaced by a hollow sphere, it can be replaced by a solid sphere, but the concept you understand is going to be the same. Correct? Okay, so break whatever object you have, break it into small charges, rotate it, find the current, multiplied by the area, and integrate. That's it. That's what we need to follow. Alright, so the correct option is going to be option A, and that is going to be our correct answer. Clear? Any problem? I hope it's clear. What was the important concept? The important concept is, what is magnetic moment? Okay, sometimes we forget. Perfect. So let's go to the next question. Alright, so far we were dealing with the force on a wire on a current carrying conductor or force on a charged particle. Now we are dealing with sources of magnetic field. So we know that current produces magnetic field. So the questions that are going to follow are going to be on that chapter. Okay. So we know that current produces magnetic field, and the magnetic field is governed by Biot-Savart law. Okay, although the correct pronunciation for this is Biot-Savart law, but we can skip that. You can say it as Biot-Savart law. So it is governed by Biot-Savart law. Okay, so I hope you remember what is Biot-Savart law, and then of course we are going to use that. So let's go ahead with this question. Okay, so what is the question? So a lot of things said in the question. Okay, the diagram is telling you everything. Okay, the diagram is telling you everything. The current is like this. Okay, so we have two wires. So the wires are bent. The configuration is clear. Okay, the distance OP and OQ is given to you as 4 centimeter, and the magnetic field is given to you as 10 to the power minus 4 Tesla. The magnetic field is given to you as 10 to the power minus 4 Tesla at point O. So what we have to do is, the current is the same in both the wires. So what we have to do is, we have to calculate the current and we have to calculate the direction of magnetic field. Okay, is that clear? That's the question. We have to calculate the current and we have to calculate the magnetic field. We have to calculate the direction of magnetic field at point O. Is the question clear? Check, let me know if it is clear. Okay, so before we get into how to solve this question, I want to know from you, what is the magnetic field? How do we find the magnetic field due to a straight current carrying conductor? How do we calculate the magnetic field due to a straight current carrying conductor? That's my question to you. And I'm waiting for your answer. How do we calculate the magnetic field due to a straight current carrying conductor? Okay, this is our straight current carrying conductor. We have to calculate the magnetic field at this point. How do we do that? Let's say the current is I. Mu naught by 4 pi I dl cross R divided by R cube. Absolutely, that's Biot-Savart law. But we use Biot-Savart law to come to a simple formula. Okay, we do come to a simple formula. What is that simple formula? You connect it, you drop a perpendicular. So if you have to calculate the magnetic field at point P, you drop a perpendicular and let your perpendicular distance be D. Okay, then you join the ends of the wire. We are going to call this angle as theta 1. Okay, so you join the ends of the wire, and this line over here, whatever it is, the angle it is making with the perpendicular, we are calling it theta 1, and this angle we are calling theta 2. Let me shift D over here. So the magnetic field is given by mu naught upon 4 pi D into sine theta 1 plus sine theta 2. Guys, go back and you can check this derivation. Okay, it would be in any book, any standard book, your notes, anywhere this derivation would be there. So mu naught upon 4 pi D sine theta 1 plus sine theta 2. That's all we have to remember. Okay, if we remember this, we can calculate for any special case. Okay, so let's do the calculation for any special case. Let's say we have infinitely long wire. So if we have infinitely long wire, this angle theta 1 and this angle theta 2 both are going to tend to 90 degree. Think, if it is infinitely long, this angle will become larger and larger and it is going to become very close to 90 degree. So for infinitely long wire, theta 1 is equal to theta 2 is equal to 90 degree. Correct? You substitute it, you are going to get B is equal to mu naught I upon 2 pi d. Is that correct? Okay, so this is a standard result also. This is a result we should remember also. But what happens is there can be many cases. There can be infinite wire, there can be semi-infinite wire, there can be any configuration of wire. So all you have to remember is this, and then you can derive that very quickly. Now suppose in this situation I have a semi-infinite wire. What does semi-infinite wire mean? Semi-infinite wire is going to mean that one end is here, one end is at a finite distance, and the other end is far away. In that case, what is going to happen? In that case, theta 1 is going to become 90 degree and theta 2 is going to become 0 degree. Can you check? This angle theta 1 is going to become 90 degree and this angle theta 2 has become 0 degree. In that case, the magnetic field is going to become mu naught I upon 4 pi d. Do you agree? Right. So if you remember this, you're going to calculate for any situation. Okay, that's what I wanted to revise for you. Clear? You remember this relationship, you can just substitute the value of theta and you can find the magnetic field for any configuration. Okay, now let's apply this. Now let's apply this question. Where are you? Yeah. Okay, now quickly, can you tell me what is the magnetic field due to the length of the wire LP? Quickly. What is the magnetic field due to the length of the wire LP? Due to the segment LP, what is the magnetic field? And I want to know from you what will be the magnetic field due to QM. What is the magnetic field due to LP? What is the magnetic field due to QM? Can you quickly tell me? Come on guys, quick. What will be the magnetic field due to these two segments? Let's first understand that. Zero. Absolutely, because they are lying on along the direction of the wire itself. Okay, so remember Biot-Savart law. So you take a small element dl, and if you have to calculate the magnetic field at point position vector r, then this is the direction of current. Okay, so what is Biot-Savart law? This is mu naught upon 4 pi I dl cross r upon r cube. Remember guys? Okay, this is Biot-Savart law. Now if this point P becomes over here, then the angle between the length and the radius, and the position is going to become 0. Hence the cross product is going to become 0. Okay, so for any wire, if you have the point along that wire, the magnetic field is going to be 0. Okay, but remember the fundamental concept also. So because of the segment LP, it is 0. Because of the segment QM, it is 0. Now what is this SP? What is this segment SP? Okay, first what will be the direction? How do we find out the direction? So I'm going to turn like this. Yeah, I'm going to turn like this. So I'm going to take my thumb along the direction of the current, which is PS, and then I'm going to curl my fingers. Now when I curl my fingers, it goes into the plane of the screen. Can you see that? So the magnetic field is going to be into the plane of the screen due to PS. And what is this? This is a semi-infinite wire. Do you agree? And what is this distance? This distance is d. So if this is a semi-infinite wire, we have just seen that it is going to be mu naught I upon 4 pi d. Agreed? Okay. What about QM? Now let's think. Now I'm going to put my thumb along QM. Have I done that? Yes. QN. So I've done that. Now I'm going to curl my fingers. Okay. Now if I curl my fingers, what do I see? I think the direction has been changed. I think that's not the correct direction. I think the question, let's check the question once. Okay, sorry, it has to be like this. I'm sorry, I made the wrong diagram. It has to be like this. Don't worry, it's correct. Okay, so QN, I'm going to place it like this, and then I'm going to curl my fingers. Okay, so when I curl my fingers, what is it going to be? It is again going to go into the plane of the screen, correct? Can you see that? It is again going to go into the plane of the screen. So because of the segment QN also, it is going to be mu naught I upon 4 pi d. And since both of them are in the same direction, the net magnetic field is going to become mu naught I upon 2 pi d. Correct? Okay, and it is given to us as 10 to the power minus 4 Tesla. Clear? Okay, Bhumi. Bhumi is saying, I have a doubt. Yes, Bhumi, please tell me. What is your doubt? My voice is not audible. Try refreshing. Try refreshing your screen. It should be audible. Okay. So we have calculated what is the we have figured out what is the magnetic field, that is equal to 10 to the power minus 4. And if we do the calculation, I is going to come out to be 20 ampere. Is that correct? I is going to be 20 ampere, and we have calculated what is the direction of magnetic field. Okay, the magnetic field is in the plane of the screen. Alright, so Captain Jack Sparrow is saying there is problem in the direction. Okay, problem in the direction of the magnetic field. Okay, let me clear that for you. Okay, so what I'm going to do is I'm going to take my thumb. Okay, I'm going to take my thumb in the direction of current, and then this palm is going to face towards the point. Okay, where is the point? The point is over here, near my middle finger. Okay, so the thumb along the direction of current and my palm towards the point at which I have to calculate the magnetic field, and then I curl. So what is this? This is going into the plane of the screen. Correct? Any problem? Okay. Okay. Next, what we do is, next probably I have to show it to you like this. Okay. Now my thumb is like this, right? Yes. So my thumb is like this along the direction of the current, and then my palm should face towards the point at which I have to calculate, which is this point. Can you see that? In your screen, can you see that? Right? It is over here. And then when I curl my fingers, it goes into the plane of the screen. So both due to PS and QN, the magnetic field is going to go into the plane of the screen. Okay. So Swali is asking, please explain 20. Very simple. From here, just do the substitution. I've not done the substitution, that's all. You can do the substitution and you can find out that the current is going to come out to be 20 ampere. That's it. Okay, if you want me to do it, I will do it. So mu naught is 4 pi into 10 to the power minus 7 into I divided by 2 pi into d. D is 4 centimeter. So 4 into 10 to the power minus 2 meters. So this is 10 to the power minus 4. So what goes away? So this becomes 2. This becomes 2. This becomes 10 to the power minus 5. 10 to the power minus 5 goes over here. This becomes 10. And hence we get I is equal to 20 ampere. Okay. So the value of current is going to be 20 ampere, and the direction is going to be of magnetic field is going to go into the plane of the screen. Okay, so option D is going to be our correct option. Is that clear, guys? Alright, so that is it for this session. But what I also want you to do is go back and try to calculate magnetic field, or try to solve questions where you have to calculate magnetic field due to a circular wire, due to an arc. Okay, that is also a very important part. So that is something we could not do in this session, but you can go back and you can practice that part also. Okay, that is also very important. Alright, so I'm going to end the session right here. I hope this was helpful for you. I hope it helps you create your concept checklist and you're able to go back and revise your weak or forgotten concepts. Okay, that's the objective of these sessions. Great to have you guys come over and over for these sessions. It's very, very encouraging for us, and I'm going to see you very soon in the next session. Alright, till then, keep practicing, keep getting better, and have fun with learning. Thanks for watching.